yesterday. So we started studying dynamics of our universe. And so we know that the metric has to be of this form. That's the FRW spacetime. And so the only unknown in this metric is basically what k is. And that's a discrete parameter. And also there's this scale factor a, which depends on time. So now I told you that the most general T mu, which is consistent with isotropy and homogeneity, is that of the perfect fluid, which is characterized by the pressure and the energy density as measured by the observer who is co-moving with the fluid. So if I'm co-moving with the fluid, that's the energy density I measure around myself, and that's the pressure I measure around myself. So of course, because I have homogeneous isotropic things, so these P and rho, they can be function of time only. They cannot vary as I move from place to place, so they are not functions of other coordinates. They must be functions of time only. So that's a significant simplification because your Einstein equations, which are partial differential equations, which are coupled and so on, so you have 10 of them, so now become actually just the ordinary differential equations because everything depends on time only. So that's a great simplification which is often misleading because people studying cosmology, they often ignore the complexity of Einstein equations and they just make, well, basically, they say, well, whatever we see in these ODEs, that's how the Einstein equations behave, but it's not true, right? So ODEs are very, very different from partial differential equations of Einstein equations. Anyway, so this is the result for our cosmology. So we have two equations, two independent Friedmann equations. Let's say the first one, the continuity equation, and because our unknowns are A, P, and rho, I need to supplement also an additional equation, which will be the equation of state, rho as a function of pressure. We have also seen that for many matter components, you can actually, if you form a fraction of pressure over the density, this is a constant. And so under this assumption, you can actually solve the second equation. So the second equation gives you a solution that rho behaves like a to minus 3, 1 plus w. Okay, so this is what we have done yesterday. And this basically tells you, which matter path dominates in which time. And that's the picture I was showing. This was the last picture last time, where you have matter-dominated era and radiation-dominated and lambda-dominated and whatever. It all behaves like how this guy actually falls off. So now what remains to actually be done is, so we have employed this guy, we have solved this guy. So the last thing is actually really to find how A behaves this time. And that's what the last equation gives us. Okay, so let's do it now. And so for simplicity, I will again do it for a single component universe. So I'll just fix W basically. Okay, so we want to find a solution of the last equation, and it's actually easier to solve instead of solving it in time t. It is easier to solve the equation in conformal time eta. So solution A as a function of eta for single component universe okay. So what it means is that we have to solve that first equation provided that rho is given by a to minus 3, 1 plus w. Or in other words, if I just reshuffle it a little bit, we have to solve a by g1 over 3 times rho equals to h squared plus k over a squared, where rho equals to some density at some time. For example, now a over a0 minus 3 1 plus w. So this is our task, and we want to find a solution of this equation. And because I told you that it's better to do it in conformal time, so the first step which we have to do is we have to switch to conformal time. Okay, so let's go from t to eta. And at the same time, let's seek a solution for A, which is some constant times, well, okay. So this will be our trick how to obtain the solution. So A will be set to a constant A times B to some power alpha, which I will choose so that it actually simplifies nicely, and that will be function of eta. Okay, so this is my simplification. So of course, you are making things more complicated, but then choosing alpha the proper way, everything will get simplified. Okay. So the first thing, so we see that there is h, so let's find what h is as a function of eta. So we know that h is a dot over a, well, which is dA over d eta over dt, which is just a dot, and 1 over a. Okay. So by definition, what eta is, this is just 1 over a, and this is just a prime. So we know that this is a prime over a square. Okay. And then plugging whatever this ansatz here. So I have to differentiate a, so it's a times alpha b alpha minus 1, and then a square is a square b to 2 alpha. So 1a cancels, and some alpha simplifies. So I have in the end that this is equal to alpha. I haven't differentiated properly. It should have stopped me. B prime. So alpha b prime divided by a b to 1 plus alpha. Okay, so this is what h is. And then you can also plug for what rho is. So rho will be rho 0, and now a over a0 to that power minus 3 1 plus w. And then a is b minus 3 alpha 1 plus w. Okay. Hopefully this is right. Okay, so now let us plug this expression and the expression for rho into this equation. Okay. Well, this is the most complicated calculation I'm doing in front of you. There will be nothing more complicated than this, but it's very simple. It's 3-line calculation, so it's very complicated. Okay, so dividing by 8 pi g3 and rho, so I get 1 on the left-hand side, is equals to 3h squared over 8 pi g Newton, and then plus 3k over 8 pi g Newton, and then I'm missing rho here, rho a square. Okay, so now we have to plug and suffer through the consequences. So what is h? So this is equal to 3, h square is alpha square, b prime square over a square b to 2 plus 2 alpha. So that's 3h square, and then I still have this guy, 8 pi g Newton, and then rho is, okay, so it's a over a0 minus 3 1 plus w, and then in the denominator I have b 3 alpha 1 plus w. So that's the first term. Hopefully it's right. Is it right? Rho 0 is still there. Something else? Okay. Keep an eye on me. 3-line calculation, very difficult. So now we have 3k, and then again 8 pi g Newton, and then rho 0, and this crap here, minus 3 1 plus w. We have also a square, which is a square b to 2 alpha. And then we still have that thing there. So it's b to 3 alpha 1 plus w. Okay, so hopefully, again, is it okay? Hopefully it is. So now you can choose your alpha. So if you look at the first term, well, all this thing is just scrappy constants, apart from b squared here, b to some power here, and b to some power there. So now you want to kill these b's by choosing the appropriate alpha. So what you want is that 3 alpha times 1 plus w minus 2 alpha equals to 0. So you want to kill the powers of b. You don't want any b's there. Okay. Yes? Why can we cancel the b? Well, okay, so at this point, I just said, well, let's plug a to b to some power alpha. Okay, so alpha is something I'm free to specify, right? So I want to specify alpha so that this is actually true, so that I have just b prime square, okay? And hopefully, this equation gives me that alpha equals to 2 plus 1, 3 w. 2, maybe 1 plus. Does it? Okay, good. So we got rid of b here. So now we know what stands here. And actually what stands there is just b squared now. So this thing here, well, with that choice of alpha, become just b squared. Okay, the second step is that I'm free to specify the constant a as well, right? So let's choose a so that this guy is equal to 1. So a squared is 3. All this crap here, I want equal to 1. Okay, which you can do. But if you look at this crap here and that crap there, they are exactly the same crap, right? So what I'm getting in the end is that your equation simplified drastically. So you still have alpha square, and now you have b prime square. And then everything else is 1, because I chose it so. And then the other term is just plus k b squared. So you have an equation 1 equals to this thing here. Okay, so now this is a very simple equation, and you can actually solve it. So just plug it into your Mathematica, whatever, and it will give you a solution that from here, the b is actually our familiar function sk, which is sine x, or sine hx, eta over alpha. Okay, so this is what your b is, if you solve it using Mathematica. So finally, our complete solution is that small a is big A times b to alpha. So of course now I've set this graph equal to 1, so I can solve for what a is, right? And if you do that, you just find that the final solution is. So the final solution is a as a function of eta is 8 pi g Newton divided by 3 rho 0 a0 3 1 plus w times alpha half. So that's just a constant in some sense. And then you have s to power alpha k as a function of eta over alpha. And remind you that alpha is whatever it is here. So it's alpha is 2, 1 plus 3 w. So in some sense, we have solved all possible evolution of your scale factor, no matter what the matter content is, in every era in one go. Okay, so this is the solution. Of course, you should receive whatever you derived in your tutorial for matter-dominated era. That's just a special case. So let me just say what it is. So for k equal to 0, then I have the component here, and again, the matter, well, density, and then A as a function of time, and A as a function of eta. So if you have matter, then your formula, well, it's 0, density goes like 1 over a cube, and then I hope this is correct, t to 1/2, and then eta. Is this what you derived in your tutorial, t to 1/2? Yes, it is, right? T to 2/3. I thought that I mixed that. Okay, very good. So t to, oh no, I have mixed columns. So what do we do? Okay, let's try to claim that this is radiation. Okay. Okay, so if I have a radiation, then I have 1/3 here. No, the columns are mixed completely. So let's hope this is right. But if it is right, then okay. Then let's put matter. Maybe somebody can check that the general formula that what I'm saying you, at least for that A as a function of eta is right. So for matter, we have 0 here. We have 1 over a cube. Now t to 2/3, and then eta square. Yeah. And then finally for lambda, you have -1. And then a to some power 0. And it's the exponential growth here, where h is a constant, and then -1 over eta is here. Okay, so that's hopefully what that formula gives you for k equals 0, maybe. Questions? So very difficult calculation, 3 lines. The most difficult one you'll see here. Okay, so we successfully reached the end of chapter 1, and I think we deserve a joke. Okay, so imagine it's animals on the train, you know, sitting quietly talking. At one point, a rabbit jumps up. Somebody stole my suitcase. Well, silence. Well, give me back my suitcase, or the same thing as yesterday will happen today. Well, they are looking, well, everybody's silent. Well, I am telling you, if you don't give back my suitcase, the same thing as yesterday will happen today. I am counting to 3. If you don't give back my suitcase, the same thing as yesterday will happen today. At that, well, 1, 2, 3. At that point, a lion stands up and so gives the rabbit back his suitcase. I'm so sorry, rabbit. I'm so sorry. I didn't know you are so attached to that suitcase. So it will never happen again. I'm so sorry. But tell me, what happened yesterday? Yesterday, I didn't get it back. All right, chapter 2. So chapter 2, and that will be matter. So here we will try to really discuss what has happened during the expansion of the universe in the early times. So section A will be brief thermal history. Brief thermal history. Not that it is actually very brief, it's quite long, but I'll just mention it very briefly. Okay. So brief thermal history. And so just to warn you, so people, parameterize this history of the universe using different parameters. So you can use the parameter, the scale as a parameter, your scale factor, so how big the universe was at that time. Or you can use the temperature of your space-time if you want. Or you can use the redshift, how redshifted the events are when they happened. Or you can just use time, let's say in seconds. Okay, so all these 4 parameterizations are possible, and so there are relations between these. So for example, I don't know, you know that T over T0 is just A0 over A. That's what we derived in our lecture some time ago. Well, this is just 1 plus Z. You can avoid this in terms of frequencies and so on. So you can basically freely go from one parameter to another. Okay. There is one particularly useful formula for early universe. So in radiation-dominated era, if you basically want to translate seconds after the Big Bang to the temperature, then you find, and maybe I'll give that as a homework, probably not. It's very simple derivation. So if you measure temperature in MeVs, then it's just approximately equal to some factor close to 1, and that's square root of the time expressed in seconds. Okay, so basically 1 second corresponds to 1 MeV, and so this is an approximate formula, but for your orientation, how to recalculate energies or temperatures in terms of seconds, this is a very useful formula. Okay, so now let me, it's something I have been preparing here, but let us go from the very beginning. So let's say that our universe started with Big Bang. Okay, so here we have the Big Bang. And this is usually, well, okay, so that happens at 0. But if you want to describe the physics around the Big Bang, you are basically hopeless to describe it because you need non-perturbative quantum gravity. Everything happens at a Planck scale, right? And so we are basically, you can say some things, but not really many things because you don't have reliable theory to discuss these things. Of course, string theory is too reliable. But anyway, so now so this is 10 to minus 43 seconds, or 10 to the 19 GeV is the Planck scale. So then there is a huge gap between 10 to the minus 43 and 10 to the minus 14 seconds, which approximately 10 TeV, where many things had to happen, or some things might have happened. But again, you don't know really whether you can trust whatever physics you know. So for example, what happened is this baryogenesis. And so it happens that for every proton, for every 10 to the 9 protons, antiprotons, so if you have 10 to the 9 plus 1 antiprotons, then you have 10 to the 9 protons, right? So for every 10 to the 9 plus 1, like, protons and antiprotons. So you have always one more proton than antiproton in 10 to the 9. Okay, so when they actually met each other and annihilated, and then you produce 10 to the 9 of gammas, approximately. and you are left with 1 proton. So this is described by this ratio, which is very important ratio and plays role in many physical aspects, which we'll discuss later on. Is this ratio of the baryon density versus the photon density. It tells you that you have so many more photons than baryons, actually. And it comes to this thing. So now, of course, there's a big question how this could have happened, right? So assume that you have created the equal number of protons and antiprotons at the beginning, right? How could it happen that actually there's always this +1, which is very, very important? If you don't have that +1, you don't have matter left, right? Everything annihilates and we are gone, right? So you know, how to get from equal initial conditions that you have equal number of protons and antiprotons, how to get this +1. And nobody knows how to do it. There are theories, there are frameworks of theories, what you need to violate in order to get it, and so on. But nobody has a consistent theory for this baryogenesis. Another thing which could have happened is if you have grand unified theories, then probably you produced some topological defects like cosmological strings, monopoles, domains, and so on. Nobody observed them so far, but it's possible. Maybe, you know, SUSY is important at these times, and maybe, very likely, the inflation happened sometime, you know, in this big region here. Okay, but this is all, you know, physics for you to be discovered. Basically, there is nothing standard in these times. Then you know that LHC can go to 10 TeV. So basically, you know, whatever happens above is already accessible to what we know. So for example, accessible by LHC. And it seems so far the standard model is actually quite a good description of what is happening above these energies. Okay. Then you have 10 to the minus 10 is the electroweak phase transition, where the gauge bosons actually acquire their mass. 10 to the minus 5, which is 150 MeV, you have QCD phase transition. So all this is very well understood. So now what is not understood is if we really have dark matter, actually when it's decoupled from the other matter, right? So that's that question mark there. So at what temperature or time actually the dark matter sort of decoupled from what we have here. What we certainly know is that the neutrinos decoupled about 1 MeV about 1 second after the Big Bang. And so the neutrino decoupling has very, you know, far-reaching consequences for our life. So first of all, neutrinos basically keep in balance neutrons and protons. Yes?
How do you know that dark matter decoupled at that point?
We don't know. I just put a question mark, right? I put a question mark. It could have decoupled somewhere earlier. Yeah. Yeah. You know, hardly later than the neutrinos, but it could have been earlier. Yeah, that's why I put a question mark there. So the neutron and proton ratio frees out because neutrinos do not couple these two anymore. And so now you are very stressed because so neutrons do not change to protons and protons do not change to neutrons anymore. But neutrons are unstable. They have finite lifetime, which is not very long. So if they are decoupled from everything else, they just start to decay, right? So you have only very few seconds to actually capture them in nuclei, right? Which is the Big Bang nucleosynthesis. So you have basically like 3 minutes to produce some nice elements. You know, if you wasted that time, then again you don't have any elements produced. Okay, so neutrino decoupling very, very important, and we will discuss that tomorrow or on Monday, depending on time. Then you have electron-positron annihilation. Again, what is left is basically like 1 electron per 10 to the 9 gamma. At the time, neutrinos were already decoupled from plasma, so which means they cannot gain anything. They are just simply decoupled, and they don't care about this annihilation. However, photons, of course, are not decoupled. Photons are produced. And basically, as electrons and positrons annihilate, they produce some energy. And this energy can be absorbed by photons. So that's why, actually, the temperature of photon baths afterwards is bigger than the temperature of neutrino baths, right? So that's a prediction of Big Bang cosmology, if you want, that the cosmic microwave background has bigger temperature than the neutrino background. But it's very, very difficult to measure neutrinos. So nobody was able to verify. So there's an exact prediction, which you will do in your tutorial, how T gamma and T nu are related. But it's, it's hard to verify. Okay, so that about 3 minutes, you boil your helium and you boil your lithium and so other elements. Then much later, 10 to the 11th seconds, finally the matter starts to dominate. So everything what actually is described up to now is basically the radiation domination. So everything interesting happens in radiation domination. And then you have radiation matter equality 10 to the 9th seconds. And this equality is important for the structure formation because structures form differently in radiation-dominated era and in matter-dominated era. So that's why this equality is quite important. But CMB was released even after that, so it's 10 to the 12th seconds. And basically, so you have now energy so little that electrons can be captured by protons and form a neutral hydrogen and not neutral helium and so on. And so in the end, once this happens, photons stop bumping into the electrons like crazy, and they can basically roam free, and the CMB is released, and the photons never scatter again. Okay, and finally 10 to the 16, 10 to the which is now, you see galaxies and other big objects, and these were mostly formed by gravitational collapse from initial inhomogeneities in your plasma. So honestly, you guys, you were not formed by gravitational collapse, but bigger objects like galaxies were. Okay. Okay. So this is a brief history of the universe, and then we will discuss these points a little bit more later on, or in your tutorial or in your homework. So this was just a brief overview of these things. Questions? All right, so let's look at some physics, how to describe these things. And so section B will be thermodynamics in expanding universe. And so my goal here is to really give you some, very simple tools. If you want to study the physics of these phenomena, how to, relatively simply estimate what's going on. How to, for example, convince you that really helium had to be formed during Big Bang nucleosynthesis. Yes?
So I have a question about at the beginning of the universe, the stress sensor is very dark, right? And so what is the motivation for the expansion? The stress sensor is dark, like the density of matter is very dark. It tends to form a black hole rather than.
Oh, very good question. I don't know. So around the Big Bang, it's very unclear what's happening, right? It's very unclear. So of course, later on, you have densities which are much smaller than forming a black hole. But yeah, I don't know. Yeah, you have to, yeah. In some sense, you have to avoid the singularity, right, somehow. So yeah, which is pure quantum gravity phenomenon. Right? So okay, so the key things, so now let me just repeat some things you already know from your StatMech course, or should know from your StatMech course. Distribution function is 3. And I will do it very, very approximately. So if I want to calculate how many particles in the phase space I have of a given species, I just take the distribution function and integrate it over the phase space. So in a phase space characterized by particle momenta and positions, I just define that dni is the number of particles of species I is given by the distribution function Tx and P, T3x, T3p, and 2 pi. So this is a definition of the distribution function, if you want. And this is the number of particles of species I in this given volume of the phase space. Okay? So now, if you know this guy here, well, it's something cube, so it's related to some kind of volume, and it's the volume of the smallest cell you can possibly localize a particle. And it comes from basically, if you want to connect classical statistical physics with the quantum physics, then this is the factor which sort of shows up. Right? So this is really the volume of the smallest cell. So this guy is the volume of smallest cell. A particle can be localized. Okay, so this is very approximately what a distribution function is. So now, once you find what your distribution function is, you can calculate interesting quantities. So for example, you can calculate the particle density and that will be, well, Ni Tnx. And that's given by an integral. So basically, you integrate your distribution function, but only over the momentum. So d3. By the way, I'll set h bar equal to 1 as always. So it'll be just 2 pi there. So 2 pi cube and fi tx and p. Okay. So that's the particle density. You can also define what an energy density so rho I for species I, Tnx. So now when you're integrating this guy, you rather put inside the integral also the energy. So otherwise it's the same thing, d3p over t pi cube E x and p and fi. Okay. So that's your energy density. And finally, you can also define a pressure. And okay. And this is equal to d3p 2 pi cube, and then the momentum square over 3e, and then fi t p and x. Okay, so once I know the distribution function, I can calculate these interesting quantities. So now Formula 1 and 2 are obvious, right? Sort of intuitively obvious. The third one is not so intuitively obvious, but pressure is, well, if you're bumping particles into a wall, right, these particles transfer the momentum, and that's what you interpret as pressure, right? So it must be related to the momentum. To get the right units, it must be p squared over e. To get 1/3, you have to do some thinking, and it will be your homework. Okay, so I'm not going to do this difficult calculation for you. Okay.
Do these quantities transform as components of a tensor?
It's a good question. They should, right? They should.
It's not obvious, right?
It's not obvious, but they should. Yeah. Well, definitely Ni is a component of a vector. So it's like, yeah, a current density, So Ni would be like 0 component of that. And then rho I, but maybe you're right. I can particle, yeah. So this is like a current density. I have a 4 vector, and these are components of a tensor, right? But yeah. Okay. So this will be your homework. Happy times. So now the question is, how do we get this distribution function? So how do you calculate the distribution function? And so in general, out of equilibrium, you have to solve something which is called Boltzmann equation. Okay. So I'll tell you what the Boltzmann equation is in my way. I hope there are some friends of Boltzmann here, because if there were, they won't like me. Okay. So now, out of equilibrium, Fi governed by Boltzmann equation okay. So now what is Boltzmann equation? So you have dFi over dt equals to, so now Fi depends on t, x, and p, so I can differentiate. So this is a total derivative with respect to time. So this is just by chain rule dFi over dt plus dFi over dxj, xj dot plus dFi over dpj, pj dot. Okay, so this is, so now if you had no collisions whatsoever between the particles, this would be simply equal to 0. And it's a statement of Liouville's theorem, which we discussed in classical mechanics. So if you have no collisions, inelastic collisions basically, then this would be equal to 0, and it's simply telling you that the volume of the phase space is the same. Or it's just the fact that evolution in quantum mechanics is unitary. Okay. However, in real life, you get a problem here, and people put a collision term here. So this is called a collision term. And that's simply something which describes how particles bump into each other, right? And it hides all the dirty physics you don't know, right? So that's why the Boltzmann equation is the most general kinetic equation, because everything you don't know you just put on the right-hand side and hide it in this collision term, right? So of course, in order to calculate something, I need to specify what this collision term is, and that's where the real fun starts, right? And so there are many, ansatzes and so on, but this is the most general kinetic equation because everything dirty you put on the right-hand side. Okay, so you would have to do this, but I'm not going to do it. Okay, I'll say that we actually are never very, very far from equilibrium, to simplify my life. So if you are interested in how the Boltzmann equation can be solved for these processes, just look at Baumann's lectures. Okay, so he discusses, he has like one section on where he uses actually the Boltzmann equation to do some calculations. He makes an ansatz what this collision term can be, the simplest possible ansatz for the collision term, and he calculates something. So see. Baumann's lecture notes for this. What we will do instead is that basically we'll try to cope with just the equilibrium thermodynamics. Okay. Oh no. So we will assume that there is something like local thermal equilibrium okay, so universe is expanding. That means that there is really not a thermodynamic equilibrium, so not in thermodynamic equilibrium. But you may compare always like how fast the interactions between particles happen and how fast the universe is expanding. So the rate of the interaction is described, well, okay. So I can have a collision time. And if this collision time is much smaller than the time in which the universe really expands, then I have something like a thermodynamic equilibrium. Okay, so if this is much smaller than the expansion time, then I will say I have local thermodynamic equilibrium. So now what is expansion time? I'll just approximate it by TH, which is 1 over H. Okay. By the way, this is nothing else by definition of H as dt over the log of A. So basically, the expansion time, TH, measures a time in which the scale factor of the universe basically doubles, right? So really it measures how fast the expansion is going on. And the collision time is just proportional to 1 over gamma, where gamma is the reaction rate for your given well, reaction. Okay, so if this is true, then we have local thermodynamic equilibrium. And what we mean by local thermodynamic equilibrium is that we have maximal possible entropy. Okay. So this is simple. So if really I have enough time to make all the possible collisions, the thermodynamic equilibrium can be restored, right? And so on. So now what I will assume, and will be my approximation, is that if I have this local thermodynamic equilibrium, and basically whatever you learn in statistical physics, in equilibrium statistical physics is true, in particular, my distribution function is just given by the e to e minus mu I over t, and then minus plus 1, where you know that minus is for bosons and plus is for fermions. Okay, so this is your distribution function in equilibrium. Okay, so here, of course, E, I'll take these particles as sort of like very, very weakly interacting. So E is just the relativistic energy, p squared plus mi squared, and then mu is the chemical potential. So that's the equilibrium approximation which we are making here. So just a remark, it's obvious that Fi depends only on E, and that depends on the magnitude of the momentum. Yes?
Denoting by P Lorentz momentum?
Well, this is the vector p, right? So that's the spatial phase space, the spatial momentum.
Yeah, but then it's not like telling that a particle has a formal momentum and just take the spatial component.
Yes.
Because otherwise it would.
Yeah. That's right. Yeah. So thanks. Yeah. Okay. So now, because Fi is as Fi of p, then I can actually change. So you want to calculate what Ni and what energy density is and what pressure are and so on. So you want to change those integrals over p into much simpler integrals. Let's say integrals over E. Okay. So and you can do that because there's this relation here. So in particular, you have d3p is just d omega p square dp. And if you change variables using this expression here, it's just d omega e square minus m square e dE. So what it means is that, for example, the expression for your particle density Ni, so Ni now becomes, so the integral over the omega just gives me 4 pi, right? So I have 1 over 2 pi cube. So in the end, I have 1 over 2 pi square left, and it's just an integral. And then, of course, your energy can, well, the smallest possible energy it can take is the mass. So mi to infinity e square minus mi square, and then E dE. Okay? So for example, you can write your particle density as this guy, and similarly, you can do it for energy density and for the pressure. And for the fun of it, you will do it in your homework. Okay? So this is the simplification. So now I want to study, so this is a general formula, but I want to study specific examples, and namely 2 limits. I want to study what happens with the plasma when it is completely relativistic, and then, on the other hand, when it is non-relativistic. Okay, so let me study, let's say, the relativistic first. So relativistic limit. And what you mean by relativistic limit is that you say that the temperature is much bigger than the mass and then the chemical potential. So that this will be my definition of the relativistic limit. So now, if that is true, then using that formula, Ni is 1 over 2 pi square. So now, Mi is much smaller than T, so I can neglect it in that integral thing. So it's 0 to infinity. Okay, and I can neglect it in the denominator. I'll have just E square dE. Okay, and then mu is neglected, so E with an E plus minus 1 here. Okay, so now we change variable E over T, sorry. Now we change variables. E over T is X. Or dE is T dx. Okay. And then you get, well, so each E gives me 1 T. So I have T square, another T, so it's T cube, right? So this is T cube over 2 pi square, and then just a dimensionless integral from 0 to infinity x squared dx, e to the x plus minus 1. Okay, very good. So now you open your tables or your Mathematica, and it will give you that this integral actually can be calculated, and is given by a zeta function. So this thing is either 2, and I don't know how to write zeta, so sorry for that. So 3 for bosons, and it's 3/2 zeta of 3 for fermions. Okay, so you conclude that in relativistic limit, your particle density is just, well, it's t cubed, so it is zeta 3. Zeta is not. Is this maybe zeta 3 t cubed over pi square, and then for the bosons, and for fermions it's just 3/4 of that. And you can write similar formulas for your energy density and for your pressure and for other things. Okay. Well, of course, it's all, well, the result is t cubed, and then there's something standing in front of that. So there's some factor in front of t cubed. Well, the fact that it's t cubed, you can immediately guess from dimensional analysis, right? So dimensional analysis, well, because you are using the units where k equals to 0, k equals to 1, h bar equals to 1, and so on. So I'll have h bar equals to c equals to kd equals to 1, which means that the energy has the same units as temperature, has the units of 1/length. Okay? So then you know that the particle density is actually a number of particles per volume, right? So volume goes like length cube. So that's why the particle density must go like something t cube, right? The energy density is the particle density multiplied by energy. So it must go like t to the 4. And the pressure has the same units if c is equal to 1 as the energy density. So pressure must also go like t to the 4. Right? So basically you know this immediately, and it's because the only energy, well, the only thing which has the right units of energy is the temperature. Right? So once maybe the mass is important, once the mass is has comparable energy as the temperature, then you can have some fractions, right? So mass can contribute to energy, or the chemical potential can contribute to energy. But at this limit, when T is much bigger than anything else, this is all I have. Okay. Questions? Can I do one more calculation? So that was the relativistic limit. So let me look at the non-relativistic limit, and then let me finish. Okay. So second non-relativistic limit. So now I'll say that the temperature is much smaller than the mass of the particle, and also assume that the chemical potential is smaller than the mass of the particle. And in that case, you can neglect the plus minus in the denominator of your formula for F. So for example, Ni is equal to 1/2 pi squared. then mi to infinity e square minus m square, square root of that, e dE, and then just writing the exponential e minus mu I over t and neglecting this plus minus 1 there, okay? So now the trick is, well, to get the right result, you have to expand in something, and that something which you want to expand is parameter u, which is e minus mi over t. So you might think that e minus mi is a good parameter, which will be small parameter. So if you have energies which are slightly bigger than your rest mass, then e minus mi is indeed small. However, t is small as well. So you know that indication is not very good. But anyway, so this is a good expansion parameter to make, as we will see in one step. Okay, so which means that E equals to Tu plus Mi. Okay. So now if you plug everything in, so you basically split this exponential now E minus Mi and then Mi minus mu I. Okay, so this is equal to 1 over 2 pi square, and then you can take this exponential mu I minus mi over t out, and then from 0 to infinity, and then, well, I have e square, which is this square, so it's u square t square plus tu t mi, and then m cancel, so that's e square minus m square, square root of that, then e is just tu plus mi. Then from differentiating dE, you get t du, so you have another t here, d du. And finally, in the denominator, you will have e to the minus u. E to the minus u in the denominator. Okay, so I just plug it in. I just chose that u that will parameterize, and then I'll just plug it in, whatever is there. So now, look, you have an integral from 0 to infinity. So if u, which you want to integrate over, is very, very large, right? So if I am integrating here, then I am exponentially suppressed because of this guy, right? So basically, what you can say is that for very, very large u, whatever the powers of u are in here, they don't matter. Okay, so now we can approximate. So keep lowest order in u, because as e to the minus u factor is there, then I can approximate. So this is already u square. So I have to keep this term, but I can cancel that term here. So then approximate this guy as 1 over 2 pi square e mu I minus mi over t from 0 to infinity. So this one I don't like, and this one I don't like. So I'll have whatever is there. So it's 2 u t mi t du e to minus u. And if you pull everything which you can pull out, you get that this is equal to mi t to 3/2 2 pi square e mu I minus mi over t, an integral from 0 to infinity tu e minus u du. So now anybody can tell me what the integral is equal to? Yeah, exactly. Yeah. So, yeah. It's the square root of pi half. So you find that your particle density in the non-relativistic limit is proportional to some prefactor here, right? So this is just a number. This is some prefactor here. But there is this exponential suppress due to the mass of the particle, right? So from here, I see that m is proportional to e to the minus m over t. Okay? So what does it mean? Well, it means that the thermodynamics hates massive particles, right? Something happened in its childhood. It simply hates them, so it wants to kill them, right? So the proportional e to minus m over t. So what it means is that really, if you have massive particles which are in thermodynamic equilibrium, there are none of them, okay? So thermodynamics hates massive particles. So that's the message to take home, and let me continue tomorrow. Okay.